Okay, hello everyone. Thank you for joining me today. I'm pleased to share with you a brief overview of my project on umbrella sampling and the weighted histogram analysis method, which is shortened as WHAM, in a 1D double well system focusing on enhanced sampling and free energy reconstructions. This topic is especially interesting for those dealing with molecular simulations or any computational scenario where crossing large energy barriers become a bottleneck. First, I will start with the introduction and motivation, and let's consider the importance of free energy calculations in fields like molecular biology, chemistry, and material science. The free energy landscape is often the ultimate guide to understand the stability, reaction pathway, protein folding, and even phase transitions. For instance, if you want to know why a particular protein adopts a certain shape or how two molecules bind together, the free energy profile can give you critical insights. However, the challenge is, which is highlighted in red here, is the unbiased molecular dynamic sampling. It can get stuck in a low energy well. Imagine a system with two deep wells separated by a tall energy barriers. In a straightforward simulation, the particle or the molecular system often remain in one well for a long time because the transition between wells are rare and slow. You end up with incomplete sampling. As a result, you can't accurately capture the entire free energy landscape. And this is where the biased techniques, this is commonly called enhanced sampling methods, come in. By introducing an external bias, you can encourage your system to explore regions that might otherwise be energetically inaccessible. Among these methods, umbrella sampling is a particular popular approach because it allows you to slice up the reaction coordinate into multiple windows, apply a restraining potential in each, and then collect well-distributed data across all regions of interest. Later, you can use WHAM to remove the artificial bias and reconstruct the unbiased free energy curve. And to illustrate the technique, I use a 1D double well potential, often written as Vx equal to 1 over 4 x4 minus 1 over 2 x2. And this function has two minimal near x equal to -1 and x equal to 1, with a significant barrier around x equal to 0, and as shown in this figure here. It's a simple system, but it's excellent for demonstrating how umbrella sampling can tackle the problem of getting stuck in one well. And in the simulations, if this is unbiased sampling, you can see that the sampling data which showing red dots are usually trapped in one well instead of um, getting into any other places. And here's the umbrella sampling setup. Um, First, divide the reaction coordinate, which is a x-axis, into overlapping windows. Each window is certain on a specific value x naught. In the typical double well setup, you might use about 11 windows, covering from the left well into the right well, ensuring the overlap in between. And and the second step, yeah. And then you apply a harmonic bias in each window. The bias potential is given by U bias x equal to 1 over 2 k times x minus x naught squared, where k is a force constant. For instance, I use 50 in a coding, and this harmonic umbrella confines the particle near the chosen window center, forcing it to explore that region more thoroughly. And then I simulate each window separately, collecting histograms of the particle's position. This ensures I get ample data from region that under unbiased conditions might be visited only rarely or not at all. And the key point is the overlap among windows. they must slightly extend to each other's ranges so that you can stitch them together later without gaps. And then is a core equation of WHAM. Once the umbrella sampling runs are complete, we gather a set of biased histograms, each one reflecting how often the particle visited certain position within its window. But these are not true probabilities of finding the particle at those positions in an unbiased simulation. That's why the WHAM is useful. Its core equation basically says we can extract the unbiased probability, which is Px here, by combining all these biased histograms appropriately. Each window has a free energy offset parameter, often denoted as Fi, here determined iteratively. We keep adjusting these offsets until the probabilities converge consistently across overlapping windows. The result is a simple, continuous, unbiased estimate of Px. Finally, we convert the probability into free energy via this equation. And we usually shift it so that the minimum of the Fx is set to 0 for easier comparisons. And here is a preliminary results. And from the umbrella sampling simulation, the first track is to look at the window histograms. And if everything's working correctly, each histogram should have its peak near the window center, but with enough overlap into adjacent window, which is the case here. And good overlap means the algorithm can have enough information to adjust the free energy offsets properly. And then I apply WHAM to yield a reconstructed free energy profile. In the double well example, you will see the two basins at -1 and 1, plus a barrier in the middle at 0. If we compare the theoretical double well, which is shown in blue dashed line here, with the reconstructed line, which is the red dots, you can see that they match closely. And this confirms that combining umbrella sampling with WHAM can accurately capture the free energy shape despite the large barrier. And finally is the discussion and the future work. At this point, I can discuss a couple of key observations. The first is convergence. The accuracy of the WHAM solution depends on having sufficient sampling in each window. If you don't simulate long enough, your statistics will be poor, leading to noisy estimates. And convergence criteria, such as changes in the free energy offsets below a small threshold, helps to ensure reliability. The second is sensitivity to parameters. The choice of force constant K and the spacing of the window centers can impact the quality of the results. Too large or too small K might either prevent adequate sampling within each window or lead to insufficient overlap. Looking to the future, it can be extended to a higher dimensional system, or we can consider adaptive or self-adjusting windows where the simulation automatically refines where to place windows or how strong the bias should be. This can reduce computational effort by focusing sampling resource more efficiently. And overall, the takeaway is umbrella sampling and WHAM work hand in hand to overcome high energy barriers and reconstruct free energy surfaces. Even though I've illustrated it here with a simple one-dimensional potential, the principles can carry over to more advanced molecular systems. And that's all for the presentation today, and thank you for listening.